In this module, you will learn the functions, operating principles, and design of hydraulic cylinders. The following learning objectives are to be achieved with this module. You should be able to explain the basic relationships between velocity, flow rate, piston force, piston surface area, and pressure. You should be able to name the functions of hydraulic cylinders within a hydraulic system. You should be able to describe the design, construction, and operation of a hydraulic cylinder. You should be able to differentiate cylinder types by their operation. You should be able to differentiate design types and state their basic applications. You should obtain an overview of the most important technical specifications. You should be able to explain the operating principles of end position cushioning. You should obtain an overview of air bleeding possibilities. You will be provided in this module with multiple opportunities to check your own learning progress at regular intervals. Your performance in these tests is neither stored nor evaluated. You have the possibility either to repeat these intermediate tests or to skip them completely. The hydraulic cylinder fulfills the role of consumer in a hydraulic circuit and belongs to the functional group energy converters. It converts hydraulic energy into mechanical energy. It carries out translational, that is, linear movements through which forces are transferred. It is therefore the link between the hydraulic circuit and the working machine. The maximum possible cylinder force, F, is dependent on the maximum operating pressure, P, and the effective piston area, A. The cylinder force is the product of P multiplied by A. A hydraulic cylinder can generate its maximal cylinder force continuously from the beginning of the stroke movement until it is completed. A simple limiting of the stroke power is possible with a pressure relief valve. The extension and retraction speed are dependent on the flow rate and the effective piston area. With lower flow rate, the piston rod extends slowly. With higher flow rates, the piston rod extends quickly. The design of hydraulic cylinders depends to a large extent on the various applications. Common functions of hydraulic cylinders are lifting, lowering, locking, and moving of loads. The most important criteria when selecting a cylinder are stroke length, speed, force, mounting position, effective direction, type of mounting, buckling effect, attachments and accessories kit, for example position measuring system, and medium, hydraulic fluid. The most important components in a hydraulic cylinder are the cylinder barrel, the cylinder cap, which encloses the cylinder barrel at one end, the piston, which travels within the cylinder, the piston rod, which is attached to the piston and transfers the piston force, the piston mount, which keeps the piston fixed on the piston rod, and the cylinder head, which closes the cylinder barrel at the other end. The piston and piston rod are provided with seals. In order to protect the rod seal and to minimize the entry of dirt into the hydraulic system, an additional wiper is required. Both the piston and piston rod are guided during the extension and retraction. The cylinder is connected to the hydraulic system via ports located at the cylinder cap and the cylinder head. These ports are generally designated as A and B, with port A located on the cap side and port B on the rod side. During extension, hydraulic fluid is supplied to the cylinder from the hydraulic system via port A. Therefore, port A is the supply port and port B becomes the return port. During retraction, port B becomes the supply port and port A is the return port. some of the components just in discussion can be identified in the complete assembly of hydraulic cylinder. When the complete assembled hydraulic cylinder is installed in a hydraulic system, it converts hydraulic energy into mechanical energy. Depending on the construction type, a hydraulic cylinder can exert forces in only one or two directions. We therefore distinguish between single-acting and double-acting cylinders. Single-acting cylinders can only exert force in one direction. The retraction of the piston can occur only by a spring tension or through the weight of the piston itself or by the action of an external force. Single-acting cylinders can only exert force in one direction, whereas double-acting cylinders can exert force in both extension and retraction. Our example shows a double-acting cylinder with a single piston rod. The piston can transfer pulling and pushing forces in both extension and retraction. This is the most important distinguishing feature of hydraulic cylinders with respect to their operation. The plunger cylinder is a typical single-acting cylinder with one pressure port. Its circuit symbol, which conforms to DIN ISO 1219, shows its basic function. Double-acting cylinders have a pressure port on both sides of the piston. In cylinders with single piston rod, the active piston area is different on both sides. The difference in the active piston area leads to a difference in extension and retraction forces for the same operating pressure. Such cylinders are called as single-rod cylinders. The circuit symbol for a single-rod cylinder also shows its basic function. Double-acting cylinders with double piston rod are known as double-rod cylinders, provided both rod diameters are the same in size. If both piston rods have the same diameter, then the active piston area remains the same. This means that for the same operating pressure, the forces in both directions of movement will be the same size. For constant flow rate, the extension and retraction speeds will also be the same size. The plunger cylinder is inexpensive due to its very simple construction. Since it has only a few moving parts and sealing areas, it runs with low friction. As already explained, it can only transfer pushing force. Once extended out, the piston rod is unable to retract hydraulically. Retraction of the piston rod can only occur by a spring, or due to an external force, or through the weight of the piston itself. This could be a problem if the cylinder is horizontally mounted, since the external force cannot push the piston rod back into the cylinder by gravitational force. Plunger cylinders are typically used in presses. The single-rod cylinder can transfer forces in both directions of movement. On the cap side of the cylinder, hydraulic fluid is applied to the entire piston area, and on the rod side, only the annulus area around the piston rod. Therefore, the force and the speed will vary generally during extension and retraction. For example, if area A1 is twice as large as area A2, the extension force is 2 times larger than the retraction force for the same operating pressure. It generally acts conversely with speeds. The volume during retraction at A2 is smaller than the volume during extension at A1. With constant flow rate from the hydraulic pump, the piston will move faster during retraction than during extension. If the different forces and speeds are to be avoided, the pressure and flow rate on both sides of the cylinder must be adjusted accordingly. In a double rod cylinder, the situation is altered. If the piston areas AR1 and AR2 are the same size, for the same operating pressure, the forces and movement speeds will be the same size during extension and retraction. Since the piston rods extend on both sides of the cylinder, more operating space is required. Due to the smaller active piston area, the force transferred by the cylinder will be smaller with the same pressure. One more note regarding piston areas. The two areas AR1 and AR2 need not necessarily be the same size. Different piston rod diameters results in different active piston areas and therefore different forces and movement speeds during extension and retraction. The design of hydraulic cylinders depends to a large extent on the various applications. There are basically two types of design: tie rod design and mill-type design. We will illustrate these types of design using a single rod cylinder, the most commonly used type of cylinder. In a tie rod cylinder, the cylinder head, cylinder barrel, and cylinder cap are all connected together via a tie rod. The tie rods have threads at both ends. Nuts are used to connect the cylinder head, cylinder barrel, and cylinder cap together. Tie rod cylinders are characterized by its especially compact design. They are often used in transfer lines and machining centers. Typical industries are machine tool and automobile industries. In mill-type cylinders, the cylinder head, cylinder barrel, and cylinder cap are screwed, welded, or connected tightly via bolts or retaining rings. Due to its robust design, hydraulic mill-type cylinders are also suitable for use in applications with extreme operating conditions. Typical applications are general mechanical engineering applications, rolling mills, ironworks, presses, cranes, mobile machines, civil engineering, shipbuilding, onshore and offshore applications. The range of cylinder sizes is very large, from mini cylinders in medical technology or hydraulic clamping to heavy cylinders in large presses, dams, and offshore constructions, or special designs are used. End position cushioning is often used to prevent hard piston hitting at the respective stroke ends. This feature is used to decelerate a large mass, thereby an expensive tool and the cylinder components are protected. End position cushioning is recommended at piston speeds of more than 0.1 meters per second or when moving large masses. An adjustable end position cushioning is constructed as follows. The piston is fixed onto the piston rod by means of a cushioning bush. During retraction, the cushioning bush enters the bore in the cylinder cap. The opening for the fluid leaving the piston chamber decreases until it finally reaches zero. The fluid from the piston chamber can now only drain away via an adjustable throttle valve. The cushioning effect is set at the throttle valve. The smaller the flow area is, the larger is the effect of cushioning. An additional check valve is normally installed to help the cylinder extend from its starting position. The check valve is closed during retraction and opened during extension. Hence, the throttling point is bypassed when the cylinder is extended. In the next screen, we will look at the end position cushioning operation with an animation sequence. A self-adjusting end position cushioning is constructed as follows. A tapered cushioning bush, flexible in the axial direction, is attached to the piston rod. During retraction of the piston, the cushioning bush enters the bore in the cylinder cap before the piston reaches the end of its stroke. The tapered bush is pushed against the piston rod, and the circular space through which the hydraulic fluid flows therefore becomes smaller. At the same time, the flow resistance increases as the piston reaches its end position. The cushioning bush effectively fulfills the function of a variable throttle valve. The bush is so designed that it can function across a wide variety of circumstances. During extension of the piston, the cushioning bush is pushed back against the piston. The circular space through which the fluid enters the cylinder now enlarges and flow resistance decreases. The cushioning bush now fulfills the function of a check valve. This type of end-position cushioning system provides gentle extension and retraction even during startup conditions, and therefore protects the working device, load, and the cylinder components from damage. During the system operation, the end-position cushioning setting does not need to be checked or reset, thus the system is maintenance-free. In the next screen, we will examine the operating principles by means of an animation sequence. It is desirable that the hydraulic fluid in a hydraulic system should not contain air. Air is extremely compressible and thereby impedes the function of a hydraulic system. Also, air bubbles that have entered the system can, under cavitation, cause considerable damage, for example in the hydraulic pump. In order to remove air from the hydraulic system, bleeding options are normally provided in the cylinders. A number of constructions have been created to simplify this process. In the following screen, we will look at the Rexroth patented air bleeding system. An air bleed valve is screwed into the respective drilled hole in the cylinder. The drilled hole is sealed with a protective cover. A protective cover is provided with a drill hole to allow the air bleed valve to be opened with a hexagon wrench without removing the protective cover. The protective cover ensures that the air bleed screw cannot be unscrewed too far and fall out. If the protective cover and the air bleed screw are removed, then the cylinder port is also suitable for a threaded coupling. The Rexroth threaded coupling shown here can either be used as a port for a pressure gauge or for air bleeding.